I guess we won't go through everything. Also, the rest advantages of virtualization solutions. So, of course, we have many advantages. That's why it's so thoroughly done in the industry. With better scalability, it's easy to deploy. It's also easy to move virtual machine images around. We have isolation, which is especially important for cloud providers. And you can even support historical hardware. But there are also disadvantages, as always. The performance may be impaired. It's really dependent on the virtualization solution. So some solutions available now have only very moderate losses in terms of performance. And then they may have limited usability. For example, there may be problems with traffic protection models. Basically everything which needs direct hardware access cannot be run in a virtual machine. This also covers the entire domain of industrial appliances for measuring and automation and control. So, for example, if you have industry robots, so you cannot steer them in the virtual machine. Here, the idea because the latencies are much higher and also more unstable because you have this layer in between. You should keep in mind that you must patch vulnerabilities in the containerized software as well, so not only in the host operating system, but also in the containers, and this can sometimes be difficult to track if you have multiple containers, because all software which is in the containers must be patched as well. This can be troublesome and difficult to track. Of course, you have some additional layer of complexity, so you have a higher overall complexity, because now you have something which is not executed in a direct way, but you have these indirections created or imposed by the virtualization environment, and they increase the overall complexity, and it's also, of course, an additional cause of failure. So there may be errors which only happen because of using virtualization, such as the compatibility issues. Then it's not suitable, as I said, it's not suitable for applications with very hard access. Also any kind of real-time application. Because we just cannot easily guarantee any kind of intelligence runtime. It also creates new attack vectors because the isolation is not perfect. And for example, there are so-called timing attacks where you can actually find out something just by measuring how long the command takes to complete. So you can derive something about the other containers or other virtual machines even. So this is mostly theoretical right now, but there have been some attacks being introduced which could also cause a real threat. So you should monitor this because if you have very critical data which have high security requirements, then they should rather be put in a physical machine than just in a container. Physical machine which is very comparable with other containers of our customers. Okay, so summary would be para-virtualization is often used by cloud providers such as Amazon Web Services with a custom operation system, so it's a kind of adoption system. The full virtualization enables you to use unmodified operating systems. The partitioning requires special hardware and firmware, so it's only used in special cases like cloud native platforms. The hardware emulation enables you to run historical software at a very high performance cost. It's often used for all game consoles and basically everything where the performance cost doesn't play a role because recent systems are so much faster that it just doesn't matter. So several orders of magnitude faster. So the performance loss is acceptable. Application virtualization is the basis for managed languages, such as Java, but also C#. Yeah, as I said, there's this Microsoft Common Language Runtime, which is pretty much the same concept as the GVM, which are able to prevent invalid memory access. So that's the basic feature of managed languages, yeah, like Java or C#, that you're unable to actually directly write to the memory. So this will prevent a lot of bugs and also contribute massively to the stability of the software. Hardware virtualization allows you to run unmodified host operating systems in an effective way. And containerization, often done by Docker, is a lightweight form of virtualization which usually isolates applications running on the same operating system. So this is the preferred basis for many cloud services because it's very, very lightweight. And still, because of the isolation, the application within the container cannot affect the other containers. At least in theory, as I said, in practice, it may happen that they can. They shouldn't. Then for AWS, AWS offers especially two services for the managed, controlled usage of large number of resources, and these are the Elastic MapReduce or EMR for the management of clusters, which consists of virtual machines on the EC2 basis, or Elastic Computing Cloud. And these use the EBS values, the Elastic Block Storage, as a block device and as S3 buckets for large amounts of application data. So EBS volumes are basically behave like any kind of flyable block device. So basically just like an SSD or hard drive which is attached to a system. So you even need to format them before you can actually use them. And they can be used for any kind of efficient disk storage. And S3 is a kind of virtual file system for storing very large amounts of data in a very cheap manner. And can actually access directly from AWS. However, EBS is much more expensive, of course, than cost. That's a real piece we use there. It costs you money as long as the data exists. Then Lambda is a function as a service, yeah, or event-driven serverless implementation of applications, which automatically scales resources. So it's quite nice that we have an automatic scalability, and it's linear, yeah? So we don't have to actually care for the deployment or the provision of new servers. It will just scale up dynamically behind the scenes. So the more function calls you have, the more you will pay, but only in a linear manner. And, so you don't have to care about provisioning at all. But of course it comes at a premium, because behind the scenes, of course, this is executed by virtual machines. So, then the services are controlled via web consoles, REST interfaces, command line tools, and APIs, which are available for Java, but also for other languages like Python. And basically all of these options use the REST interface. So there's the REST interface, and everything else like the command line tools actually are just called the REST interface. The costs are roughly proportional to resource usage. especially regarding working memory, so RAM. That's also CPU time, data transfer, storage, and for Lambda also I/O load. For Lambda is also important what the top memory usage of the process is because it will determine the price to a large extent. So it makes it very useful for planning business models, because you can exactly predict that if you have twice the customers, then you may have, for example, twice the resource usage. So it will maybe cost twice as much money, about 4 times as much. So it's usually proportional, it's linear. And if you're working with AWS, always use S3 for write data storage. It's by far the most cost-efficient storage for large amounts of data. For serverless computing, of course we have many advantages, so we don't need any more server management. For step cost, as I said, no additional virtual machines being deployed. It's scalable, usually without having you to do anything. You can also easily deploy any updates, and also it's very quickly to implement services based on serverless computing. But the largest disadvantage is actually the vendor lock-in. So if you have deployed something on the serverless computing platform, it's really impossible to move the entire application to another vendor. And it's also quite difficult to debug and test because it's being executed on the cloud side, not on your side. And it's also potentially susceptible to vulnerabilities because the code is usually running a massive parallel manner. So many other customers are running the same code on the same physical machine. And of course, it becomes even because it is abstracted of the hardware, but still behind the scenes, of course, it's still hardware. Then we talked about web reuse. Web reuse is basically an application of the split apply combine principle. We have this nice image here, so of the Lego. So here is the Lego bricks, and the idea is that you have a breakdown of the data set into groups according to special criteria, like here is the color of the shape of the bricks. And then we line a function in each group. And finally, we create an aggregate of all results, which is an overall result like this aspect here. So that's the basic idea. And because we have separate groups, we can now parallelize everything on the level of the individual groups. And how is it implemented in web reuse? So in the basic view, we have these 3 steps. We have a map step, we have a shuffle step, and we have a reuse step. And for the mapping step, every node applies the map function to its local data, so the data comes from the node using a mapper. So the mapper is a component which applies the mapping. And then it writes the result into a temporary storage. And then the master node ensures that redundant encode data are only processed once. So it will guarantee that the data are only processed once. And then we have the shuffling step where the data are redistributed among the nodes, depending on the result of the map function, of course. So that the result of the mappers now become the inputs of the users. But of course, the data are only redistributed if the functions require this. And then in the reduce step, the results of the map function are sorted and partitioned, so that then they can be consumed by the reducer, and the reducers create the reduction. So the reduction is basically unification of the results. So what are the components of Hadoop web reuse which can be customized? First, we have the input reader. The input reader divides input data into manageable parts, which are like 64 megabyte each. And these are then directed to a map function, and the data are read, for example, from a distributed file system, such as HDFS. So HDFS stands for Hadoop distributed file system. And they are transformed into key-value pairs. So Hadoop is always working on key-value pairs and then transformations of key-value pairs to another key-value pair. The map function also obtains a set of key-value pairs. It applies the mapping function to every value. Thereby it will create a result pair of an arbitrary key, which is often the same one, and the transformed value. And also important to note that the cardinality of the input and output data sets need not be identical. So the output of the function may yield more elements than the input. And then we have a partitioning function, which assigns the output of the map function to a certain reducer based on its key. And this aims to achieve a uniform distribution of the keys among all reducers. And finally, we also have the shuffle components, so data are moved from the creating node to the node which is scheduled to move to. So this was first covered by the partitioning function. We have a compare function for the definition of equality. This is required for sorting the input data, which is done in preparation for the reduction step. Then the actual reduce function is called once per key in sorting order, and it iterates over all values which are assigned to its key. So it may create a single output element, but it may also create multiple output elements, or it may create no output. So the result of the reduce function there is simply nothing. For example, in the word count example, we have input pairs where every branch is assigned to its count, so the number of occurrences, and the output pair would then be like the total count of this structure. So this would be a single node, and this would be the total word count for this word over all nodes. And then, we may also have a combiner function. The combiner function is optional in terms of we can use the same reduce function for this. So in this case, we just set the combiner function to the reduce function. So this usually works, yeah. So it's basically the same, but it's called a single node prior to the reduction step. Yeah? So of course, we want to reduce something locally before we need to reduce it globally. Yeah. So the combiner function will do the local reduction, and then the reduce function will do the global reduction. And quite often we have we need the same, so because most of the times. And then we have an output writer, which writes the results of the reduce function to the persistent storage, so we can actually get them up there. We had some constraints for the reduce function. So basically associativity and the neutral element. Associativity just means that if you have something like A is related to B and you have C, then it's the same as the other order. For all A, B, and C are also very interesting function. And the neutral element means that just there's one element in the set which is invariant towards multiplication of functions. So, for example, multiplication would be 1 and for addition it would be 0. And the neutral element must exist so that nodes which don't get any data do not affect the result. Yeah? Because otherwise, if we would reduce the result of nothing with another result, then it would impact this result, which we don't want. So that's why we need to have a neutral element. And this is basically the same as the algebraic structure of the monolith, consisting of the set and the neutral element is the duration. And in this case, the set is the duration. And yeah, we are that not all possible binary functions, of course, satisfy these conditions. Yeah. For example, the average function is not associative. Because if you look at the average of 1, 2, 3, then if you first create the average of 1 and 2 and then of 3, it would be 2.5, but if you create the average of 1 and then of 2 and 3, it would be 2.75. Yeah, so it really depends on the way it's flat. Yeah. So be aware that this doesn't work with all functions. And yeah, we also don't have leaf average of average. Yeah, so with average out of 0 and anything, it won't be anything until the half. So there are of course more functions which don't work like the average function. About the performance of MapReduce, I need to find a balance between the costs for the CPU time and data transfer. Persisting data on intermediate storage leads to dominance of data transfer costs most of the times. And the performance is basically dominated by the amount of data created by the network. So the data is created by the network, the higher the performance effect is. So if you're using Hadoop, then should if the intermediate results do fit into the rest of the node, then usually choosing Apache Spark was a much better choice, because Spark has everything in memory. So if it fits in memory, then use Spark, because then it will do memory processing. Only if, for some reason, it can never fit into memory, and you also can think of a way it should fit into memory, then they will consider using it as well. Because otherwise, Spark will always be more performant. Sometimes for a lot of applications. That's why, because the concept of Spark is that failing tasks are rerun, so you will just discard calculated results if the task is failing, but thereby it doesn't need to persist the data. And MapReduce, they can be restored, and I mean on Spark you can also persist them if you want, but you don't need to. And in most of the cases, it's just not, it won't give you a performance gain to persist the data, because recalculating them is faster than persisting them. Then we have the Hadoop distributed file system, HDFS, which is also the basis for Spark. Yeah, so it's also commonly used with Spark. And yeah, it's distributed, it's scalable, and it's portable. Yeah, I mean distributed means that the data are spread among different nodes in a redundant way. So basically it has by default this three-fold redundancy. Every single data point is at least replicated 2 times on other nodes, which makes it quite safe to use. Against data loss, then also it's scalable, so it works from very small to very large. And it's also portable, which means that it's quite easy to actually pick all the data and deploy them somewhere else, because it's somewhat very simple structure. So distributed, scalable, and portable. It's fully implemented in Java. It has these 5 services, so it consists of so-called master services and slave services. Master services are the main node service, the secondary main node service, and the tracker. And the slave services are the data node and the task tracker. Basically, the main node is there only once, and it has all the metadata for all the stored data. And your HDFS client doesn't directly communicate with the main node. The secondary main node is just there for some management operations, which are called by from the main node. Then the job tracker is there to accept jobs from the MapReduce framework. And then the data node actually stores the user data and it reports to the main node by using API. So the main node is responsible for monitoring the file system. And if the heartbeat is missing, then the name node will replicate data to another node. So the name node ensures that we actually have this redundancy and it's working. And it's consistent. And the task tracker will receive its tasks from the job tracker. It also receives the mapper code from the job tracker, and then it will apply it to the data. So you usually have one name node, and you have a cluster of data nodes. All files are stored in this tree for redundancy, and you can mount the HDFS directly as a Linux file system. Also interesting that NetBeans can use Amazon S3 instead of HDFS. So it's then used the same way. So if you're running AWS cloud service, then you might consider directly using S3 instead of HDFS. It's only a difference in the implementation, but not for the interfaces. Then we had a discussion on Hadoop Yarn. Yarn stands for yet another resource source, another resource manager. And basic idea is that you have separation of resource management and job scheduling in different services. So you have the global resource manager and the application-specific application master, and you have a node-specific node manager. So these three components, and they work on different levels of application, you might say. And this jobs application is either a direct job or a single graph of jobs, like this. So we have numerous jobs which are connected in this graph. Yarn is this basic architecture. So we have the resource manager, which itself consists of two parts. It has a scheduler and an applications manager. So not to confuse it with the application master. So the application manager is part of the resource manager. And then we have several nodes, and each node has its own node manager. And then we have an application master for each application running on the cluster. So the number of application masters is equal to the number of applications, and not equal to the number of nodes. Yeah? So the number of node manager is equal to the number of nodes. So usually you have just one resource manager for the cluster. You have one application master for each application, but you may have more than one application required to the same resource manager, like this. So here's the application master. There's another application master. And so they both report to the resource manager. They're requesting resources from the resource manager. And the node manager is reporting its status to the resource manager. So one resource manager for the entire cluster, one application master for each application, and one node manager for each node. And there are several containers. Each container can be placed in a node, but there can be more than one container placed on the same node. And the application master itself also wants to limit container because then actually created by the resource manager itself. Because when you first need to have the application master, so that you can then request other containers from the resource manager. So the container where the application master is running is applied by the resource manager itself, but not to other containers. And the client is only talking to the resource manager. These components, a little bit more in detail. So the client submits the application, which is a MapReduce job. If you're using Spark, it will also be a job in action. And it will submit the job to the MapReduce framework. It then talks to the resource manager for requesting execution and monitoring the job status. And the application manager, the application master will report progress of the client. Then the resource manager, as I said, there's only one per cluster, consists of a scheduler and an application manager. The scheduler performs the scheduling based on the allocated application. It does nothing else, yeah, for scheduling. When the application manager accepts the application from the client, it can restart the application master container if the task should fail. So it also is responsible for acquiring the first container. So basically the application manager is the instance which controls all application masters in the cluster. And keeps track of all the applications that are being sent by the client. And then we have the node manager. So the node manager manages the individual node of the cluster and records the heartbeat in the health status. So it holds just a series of nodes if the node is still up and running. It also monitors the resource usage of this node. And it can also terminate containers if the resource master directs it to the resource manager is directed to do so. And it can also start a container process of a request by the application master. So the application master doesn't actually run the container itself, but it will request running a container from the node manager after it has asked the resource manager on which node it should ask container to be resolved. Yeah? That's because the resource manager will know which node is currently available and has the resources. Yeah? Besides the resource manager, so the resource manager has to track all resources of the entire cluster. So the application master asks the resource manager, hey, I would like to have a new container running. And the resource manager will tell the node manager, okay, so will tell the application master, okay, please use this node, and this is its node manager. Yeah? Then the master will talk to the node manager, okay, no, the resource manager told me that I should use you, yeah? And now I want to run a container, and here's all the data for the container. And then this container process will actually be started by the node manager. Because the node manager knows the resource of the node. Okay, so a little bit complicated. The application master, as I said, is responsible for application. So it's responsible for a single application. It will negotiate the resources with the resource manager and will track the status and the progress of the application. And it sends a health report to the resource manager on a regular basis. And the first step is ask the resource manager for the appropriate node manager. This works because the resource manager knows which node has the resources available. Then it will send the software container launch context to this very node manager. So everything the node manager needs to know in order to run the container. And then the node manager will just execute this and then run the container. And actually a single application master may request multiple containers. Yeah? They may be running on different nodes because the application master might ask the resource manager, hey, I would like to have two containers, and then the resource manager might say, okay, but on this node you can only run one container, please then also run the other container on this other node. Yeah. So the containers can be distributed across the cluster. But it's always that containers, except the ones, of course, where the application master is running itself. Yeah? Or the other containers are run on request of the application master. And controlled directly by the application master. It can also happen that the application master doesn't always get the resources at once, yeah? Because the resource manager might say, okay, you may want this, but I don't have the resources. So just we just put it in a queue, and then we will get the resources as they're ready. But until then, I will only give you one container, even though you would like to have two. Yeah? Then the other tasks going to wait. Yeah? Because resources are limited. Yeah? That's why we need resource manager in the first place. Okay. The container itself is a collection of physical resources on a node, which consists of the memory, the CPU cores, and the disk. In production, you have typically 10 to 40 containers per node, so it's really a lot of containers. Of course, this is to maximize the resource usage, because you have a powerful machine, then of course you need lots of containers that actually make use of the memory and all the CPU cores. So the container launch context contains all the required drivers, security dependencies, everything which the node manager must know to launch the container. And if you have a typical web business job, you have at least one application master container, of course, since that this is run by the resource data itself. So that the application master has something to run. Then you have a number of network containers, so you have one network container for each input stream. And you have a number of user containers. And when you see five line job configuration, usually it means it's one. That's one user, but several more members, and at least one application master. So usually these three containers also in modern YARN versions, you have so-called placement constraints, and these control the way of the container placement. And the default behavior is that data locality is pursued. This means that the resources are requested when the data are located, which are preprocessed, which makes more sense in most of the cases. Yes, so if you want to work on, for example, if you have the HDFS source, then of course the HDFS blocks where you want to work on should be located on the same node, so that in terms of data locality, they are directly node local, so you can access them quite fast. But you can change this behavior and you can tell YARN, okay, I want the container to run the same as the application master, or I want the containers to be run on different nodes than the application master. So why would you want this? Well, if you're running them on the same node as the application master, you have a more direct way of controlling the containers, so the application master, so the control is faster, the containers, and in the other way it would be a little more secure, because if container fails, the application master is not okay. But as I said, the default behavior of assuming data locality is in most cases what you would want. Okay, so to sum this up for YARN, we have a single resource manager, controls the entire cluster. Our client basically only talks to the resource manager, at least to a large extent. So the application masters can report some states updates to the client. The resource manager is the most important point where the client talks to. Then for every application, we have a separate application master. This controls the application. And it usually runs on a different node as the resource manager. Then for every node, we have a node manager. The node manager controls the resources of the node. The application master can request containers and often request more than one container from the resource manager. And they may be located on the same or another node than the application master itself. And which node is actually assigned is decided by the resource manager, not by the application master. The application master can only request resources, but the resource manager will decide what resource actually required. And then the application master will be directed by the resource manager to a specific node manager. So it can run the container, and then for this, the application master will send the container launch context to the node manager. Then the node manager will launch the container using the container launch context. And the application master will report its status to the resource manager. So the resource manager is always aware of the status of all applications on the cluster. And the placement of containers is decided by the resource availability as well as the data located of the nodes. So the data should be as close as possible to the code as always, and also the resource must be available of course. And the number of containers which are run per node, usually you have more than one container, like 40, so 5 containers running the same node. And it depends on the available resources, of course. But if you have a very small node in terms of resources, then it's probably not a good idea to put this in a cluster. productive environments, you will always choose a
Cái phần này thì
configuration
là cái
hardware
phần
which
ETL.
allows you to run several implementations.
Có kinh nghiệm về cái
Because it's
này.
not efficient otherwise. Okay, then we talk about components of Spark. Yeah. So ecosystem in a narrower sense, and it consists
Này
of
đang học
Spark
cái này
SQL,
là học môn của Manuel.
which is for SQL style querying of Spark. Then we have a library for machine
Chưa có
learning.
được check.
We have another library for graphs, and we have a library for structured streaming. And we have the modern Spark Core, which has
Chưa có được check
bindings
đủ luôn.
and implementations for these four languages, Java, Scala, R, and Python. But actually Java and Scala is mostly the same because it's uses the same bytecode. So there's not a big difference, all it's only different interfaces. Actually it's the same, pretty much the same implementation
Nhưng mà
behind it.
thấy đỡ hơn môn của
But R and Python isn't entirely implemented, so some parts are missing.
cái bên.
Then, we discussed different representations of data in Spark. First, the oldest way of representing data in Spark are the zero distributed data sets or RDBs. An RDB is a type set of data which is to be processed together, so it's an abstraction
Story của nó
of a
nói
set.
là đi làm những cái thuốc bụi.
And we're always aware that you're working with the abstraction of the set, but not with the set itself. So you can create it either from a local file or from any source which is supported by an interface or input format. For example, HTTPS. And as you work in the driver program, it's not really a set, so you cannot simply just speak internet or debug it or so, because it's just the abstraction of the set. So if you actually want to view the contents of the set, you always need to run the entire cluster to actually calculate the contents of the set. Then you have data sets and data frames, which are pretty much the same. It's just two different views of the same data structure. The data sets are a recent concept which is introduced with Spark SQL. Spark 1.6, so it works on top of Spark SQL. And the data sets can be generated from relational objects. It can be processed with more functional transformations. And the dataset API is available in Scala and Java, and not in other languages. And then the data frames are basically just data sets with named columns. So conceptually, they correspond to a table in the relational database. And the representation in Java is a data set of rows like this. And Spark distinguishes between transformations and actions. Transformations are performed, for example, in the web operation. Any kind of method which transforms a data item to a new data item. And actions actually trigger a calculation on the cluster to collect the results. So if you call a transformation, the transformation is basically just a mapping function. Then this will lead to nothing except the framework internally builds its execution graph, and therefore RDBs are always lazy. And so if you only, as long as you are creating, as long as you are executing transformation operations, nothing will happen except the graph will be built up. And if you have actions, then actions can only be evaluated by performing action calculations. Examples are, for example, the reduce function, but also the count function. Because we want to know how many elements an RDB has, then of course we need to do the entire calculation. And as soon as the Spark driver encounters the first action, it will create, it will run the entire cluster with this action. So this action contains all the entire graph stuff which has been built up by your prior transformations. Okay, I guess we can stop here. So some people are already leaving. Yeah, so we can continue this on the afternoon. And I guess we can available